Lesson 9-4 Polynomials. Before we go into the lesson proper, let's talk about polynomials with regards to algebra tiles. And before we even do algebra tiles, let's define what a polynomial is. So a polynomial is a monomial or the sum of monomials. Okay, so again, you need to know what a monomial is. Remember what a monomial is. A monomial is a number, a variable, or a product of numbers and or variables. Okay, and the definition of a polynomial is that it is a monomial or the sum of monomials. So definitely, if it is not a monomial, then it is not anymore a polynomial. Okay, so let's take a look at this diagram below, which shows the models of algebra tiles. So polynomials are modeled using three types of tiles. Okay, the unit tile, which is 1 unit. Why is it 1 unit? Because if you do the length of each side of this unit tile is 1 and the area is 1. That's the reason why 1 times 1 is 1. Okay, and call this the unit tile. We have the x tile. The x tile is such that the area is x. Why is that? Because the width of the x tile is 1 and the length is x. So given the area area of a rectangle, length times width, if you multiply the length and the width, will give you the area of x. And you have the x squared tile. Why is it x squared? Because again, that's the area. The length of each side of the x tile is x. Okay, x times x is x squared. Okay, that's why you have x squared. Okay, now it is important for you to remember the length and width, okay, of the x tile, the unit tile, and the x squared tile, because later on when we start adding and multiplying polynomials, that will come in very handy. So each of these tiles have an opposite. Okay, you have the opposite of the unit tile is the -1 tile. Okay, again, it can be that the length of this side is 1, this one is -1, so it's that's why the area is -1. On the other hand, you can do this as well. Okay, this can be 1 and this is -x, or it can be the opposite. This can be -1, that can be x, and this is the x squared, -x squared tile, that can be x. This will be -x to give you the -x squared tile. Okay, so these are your polynomial models. Okay, these are your algebra tiles. Okay, now let's take a look at some activities. Use algebra tiles to model each polynomial. It's saying 2x squared. That means to model this polynomial, you will need two blue x squared tiles. So two of these, 1 and 2. And this is the model of 2x squared. Okay, so let's take this one step further. Let's try x squared minus 3x. Okay, so x squared minus 3x would give you one blue tile. Okay, it's this one. Okay, let's put this on the side right there. Okay, and then since it's -3x, you'll need 3 of the red squares, 3 of the negative x tiles right there. So this is the model of x squared minus 3x. Okay, let's model x squared plus 2x minus 3. Again, x squared is a positive, so we get one blue tile, x squared, plus 2x, that's a positive, so two green tiles. Okay, and then minus 3 means 3 -1 tiles. Okay, so this is the model of x squared plus 2x minus 3. Okay, and basically this is like an algebra math where you can do all of that. So let's say we want to model uh, -3x squared. If we try -3x squared, okay, So negative 3x squared will require negative 3 of the negative x squared tile, or 3 of the red x squared tile. So that's negative 3x squared. If we do one more activity here, I'm getting this on page 513. Let's do 2x squared minus 3x plus 5. Okay, so let's do 2x squared minus 3x plus 5. So 2x squared minus 3x plus 5, since it's a positive 2x squared, we'll get 2 of the x squared tile minus 3x, that means 3 of the 3 of the red x tile. Okay, plus 5 means positive 5, so 5 of the yellow unit tiles. Okay, and this is how you model polynomials using algebra tiles. It seems very easy, but this becomes very useful later on when we start adding, subtracting, multiplying polynomials. Okay, so that's a little background of polynomials, what they are, and that's a visual representation of what a polynomial is. Okay, so let's go to our lesson proper. In this lesson, you learn to find the degree of a polynomial and to arrange them in terms of a polynomial so that the powers of a variable are in ascending or descending order. And then why is it important? Because you can use polynomials to solve problems involving agriculture and biology. But right now, let's take a look at art. The painting composition with red, yellow, and blue by Dutch painter P.A. Mondrian is shown at the right. Mondrian preferred abstraction and simplification in his art. He liked to limit his palette to the primary colors and use straight lines and right angles. The style of the painting that he developed is called neoplasticism, and he is considered one of the most influential painters of the 20th century. Okay? So consider the portion of the painting composition with your red, yellow, and blue. Okay? The length of the sides of the area of each section are given. So let's say this is the painting, red, yellow, and blue, and this is the length of the sides, X, Y, and Z, R, S, and T. It says the area of the section are given. Why? It's not given now, but I'm gonna give it to you right now. Okay, so the area of this blue rectangle will be the product of R, length R, and width R and length X. So if you multiply R times X, that'll give you Rx. The area of this beige rectangle will be the product of width S and length X, which is Sx. The product of this green tile right here, or green rectangle, is the width T and length X, which is Tx. Again, this beige rectangle is the product of width R and length Y, which is Ry. And this green one right here will be the product of width R and length Z, or you can do the opposite, width Z or length R, doesn't really matter, which is RZ. And we do the same to the rest of the rectangles. This green rectangles will be SY. This light blue rectangle will be SZ, the area that is. The area of this rectangle will be TY, and this beige rectangle will be TZ. Okay, so we can find the area of this portion of the painting by adding the areas of each section. So what it's saying is that we want to find the entire area of this painting. So to be able to find the entire area of this painting, we simply add up all of the areas, which is Rx plus Ry plus Rz plus sx plus sy plus sz plus tx plus ty plus tz. Okay, again, now remember this because we're going to use this again later on, this type of finding the area. Okay, so the expression representing the area of this portion of the painting is called a polynomial. Again, we define what a polynomial is. A polynomial is a monomial or a sum of monomials. We call it a monomial. Remember this. Again, the definition of a monomial: a number, a variable, or a product of numbers and variables. The exponent of the variables of a monomial must be positive. So one thing that we did not define earlier, so the exponents of the variables of the monomial must be positive. Okay? If it's negative, obviously it's not a polynomial. So a binomial is the sum of two monomials. A trinomial is the sum of three monomials. Here are some examples of each. So we know what monomials are: 3x squared, 2abc squared, negative 914m, because of the definition of a monomial. Binomial is the sum of these monomials. So you have 4x minus 7 is a binomial, 2x plus 9y is a binomial, all the way to 2 plus 13x. And finally, okay, you have a trinomial. Remember, in a binomial, you have only two terms. 4x and 7 are your two terms, or 4x and negative 7 are your two terms. With a trinomial, okay, you have three terms, or three monomials being added. So a plus 2b plus 4c, x squared plus 8x plus 9, x squared plus 2x, y plus y squared, 3a minus 7b squared minus 4c. So those are all examples of monomials, binomials, and trinomials. Okay? So let's take a look at how we apply this. State whether each expression is a polynomial. If it is a polynomial, identify it as either a monomial, binomial, or a trinomial. So you have 3a minus 7bc. Okay, so 3a minus 7bc. The expression 3a minus bc can be written as 3a plus negative 7bc. Therefore, it is a polynomial, since 3a minus 7bc can be written as a sum of two monomials, 3a and negative 7bc. It is considered to be a binomial. So this is a polynomial, and this is a binomial as well. Okay, so 3x squared plus 7a minus 2 plus a. Okay, again, look at this carefully. Okay, you notice you have like terms in 7a and a. It can be written as 3x squared plus 8a plus negative 2. Therefore, it is still a polynomial, since it can be written as the sum of three monomials, and this particular polynomial is considered a trinomial. And finally, let's take a look at letter C, and notice that the variable r is in the denominator, and if it's in the denominator, it does not make it a monomial. So the expression 7 over 2r squared plus 6 is not a polynomial, because 7 over 2r squared is not a monomial. Okay, and one of the conditions for it to be a monomial is that the variable, the exponent of the variable, should be positive. And if you notice, okay, when you say 7 over 2r squared, this is the same as 7, okay, over 2 times r to the negative 2. So that also is an indication that this is not a polynomial, simply because you have a negative exponent on the variable. Okay, so let's take a look at example number 2. Each of the three, okay, before we read example number 2, polynomials can be used to represent savings accumulated over several years, and this is example number 2. So each of the 3 summers before Li Qiang attends college, she plans to work as a lifeguard and save $2,000 towards her college expenses. She plans to invest the money in a savings account at her local bank. The value of each year's savings can be found by the expression px raised to the t power, where p represents the amount invested, or the principal, x represents the sum of 1 and the annual interest rate, okay, and t represents time in years. Okay, so we want to write a polynomial that represents the total amount of money Lee will have when she starts college, letter A. And letter B, we want to find the amount of money Lee will have earned if the bank is paying 6% annually. And that is actually a huge interest rate, given the interest rate that we have today. Okay, so let's write a polynomial first. By the time Lee goes to college, the amount of money she makes the last summer will be worth $2,000. The money she makes the second summer will be worth 2,000x. Okay, and the money that she makes the first summer will be worth 2,000x squared. So, writing a polynomial in this for this problem, she will have 2,000 plus 2,000x plus 2,000x squared. Why is that? Again, let's see why it's 2,000 plus 2,000x plus 2,000x squared. Because she plans to work and save $2,000 towards her college expenses. Okay. And then, where did the x come from? This is the x, where it says here x represents the sum of 1 and the total interest rate. So basically, your interest rate, okay, would be multiplied by itself, okay, after the first summer. So that's the reason why it's x squared. Okay, so letter B, find the amount of money Lee will have earned if the bank is paying 6% annually. So we simply get this. Okay, use the formula that we use, which is px raised to the t power, which is now being applied to 2000x squared, and simply substitute x with 1.06. Okay, where did the 1 come from? Because remember, on the word problem it says x represents the sum of 1 and the annual interest rate. And the annual interest rate is 6%. As a decimal, it's 0.06. So we replace x with 1.06 and calculate the amount of money Lee would have earned. So at the end, Lee would have earned, okay, $6,367.20. Okay, so she will have that much for college. Let's move on. Let's talk about degrees of monomials and polynomials. Let's talk about the degree of a monomial first. So the degree of a monomial is the sum of the exponents of its variables. Very easy. So if you look at this monomial x 8y cubed, the degree is 3y because the sum of the exponents is 3. In this case, there's only one variable, and the only variable is the only exponent of that variable is 3. So the degree is 3. Let's take a look at this one, 4y squared ab. If you notice, the exponent of y is 2, the exponent of a is 1, the exponent of b is 1. So basically, what we do is we simply add 2 plus 1 plus 1 will give you 4. So the degree of this monomial is 4. In the next example, negative 14, it does not have a variable. So that therefore the degree of this monomial is 0. And finally, 42abc. Okay, the degree of a is 1, b is 1, and c is 1. And we simply add all the exponents, so the degree of this monomial is 3. Okay, let's take a look at the degree of a polynomial. Degree of a polynomial, you must find the degree of each term. Okay, and then the greatest degree of any term is the degree of the polynomial. Again, this can be confusing, so listen up. The greatest degree of any term is the degree of the polynomial. Let's take a look at this example right here. 3x squared plus 8a squared b minus 4. So the terms of this polynomial are 3x squared, okay, 8a squared b, and negative 4. So the degree of 3x squared is 2. The degree of 8a squared b is 3. And the degree of negative 4 is 0. But the greatest degree of the terms is 3. So the degree of this polynomial is 3. Okay? Next example. 7x to the fourth, 9x squared y to the seventh, 4x. Okay, the degrees are 7x, sorry, the terms are 7x to the fourth, negative 9x squared y to the seventh, and 4x. So the degree of 7x to the fourth is 4, negative 9x squared y to the seventh is 9, and 4x is 1. So the degree of this monomial, of this polynomial is 9. Okay? So let's take a look at example number 3. Find the degree of each polynomial, 9xy. Okay? So, taking a look at this one. Okay? If it decides to show itself. So the degree of 9x y is 2. The degree of 2 is 0. Therefore, the degree of this polynomial is 2. This one, the degree of 18x squared is 2. Degree of 21x squared is 3. Degree of 13x is 1. And the degree of negative 2abc is 3. Therefore, the degree of this polynomial is 3. Okay, so pretty simple. And the final touch to this lesson, the terms of the polynomial are usually arranged so that the powers of one variable are ascending or descending order. Before we do that, let me say the secret word. The secret word for this particular lesson is knights. Knights, knights. Okay, so let's continue. The terms of the polynomial are usually arranged so that the powers of one variable are ascending or descending order. So later in this chapter, you will learn to add, subtract, and multiply polynomials. These operations are easier to perform if the polynomials are arranged in one of these orders. So again, you need to arrange your polynomials in ascending or descending order for you to be able to add and subtract polynomials a lot easier. Okay, so this is the ascending order of this polynomial. Look at the descending order of this polynomial. 2a cubed minus 6a squared plus 5a plus 4. We are looking at the exponents of the variables. So it's descending order because it's 3, 2, and that's 1 right there, and 0. So 3, 2, 1, 0 is in descending order. The ascending order, of course, would be 4 plus 5a minus 6a squared plus 2a cubed. Okay? Because you start with 0 exponent, 1, 2, and 3. Okay. Again, another example of ascending order is negative 5, negative 2x plus 4 to the fifth, 4x to the fifth power, because it's 0, 1, and 5. Okay? Descending order would be 4x to the fifth minus 2x minus 5. Ascending order of another example in terms of x in this case. So in terms of x, we're just looking at the variable x. It would be 8xy, 3x squared, x to the fifth, and x to the seventh y power. Okay, so 8xy, 3x squared y plus x to the fifth minus 2x to the seventh y, because we're looking only at the exponents of the variable x. And if we do that with in descending order, we start with negative 2x to the seventh y plus x to the fifth minus 3x squared y plus 8xy. Okay? And in terms of y this time, we only look at the variable y and arrange them in ascending order. So this one doesn't have a variable y, so that means this is 0, and this is 1, 2, and 12. Okay, and in descending order, we switch it now. We have negative y to the 12th now, plus 2x squared y squared minus 3x cubed y plus 2x to the 4th. Okay, so that's ascending and descending order. This will become very important later on in this chapter. And that's the end of our lesson. Thank you for watching.